Probability test review. So tonight, I would suggest you read over probability test review, this worksheet, a few times. It's going to be helpful because you will have a test at the end of the week. So let's talk it through. It says probability test review. Blank is a ratio that compares a number to 100. Blank is a ratio that compares a number to 100. Gavin, what is it? A percent. Perfect. Percent means of 100. Percent. A percent is a ratio that compares a number to 100. So when we began this unit way back with percents, decimals, and fractions, Colin, please stay focused. The main idea, or the first idea we worked with, was taking a percent and writing it as a fraction. Percents to fractions. So for example, let's say you got an 88%. How can what are the steps on your test you'll be asked to convert the percent, 88%, and you'll be asked to convert it to a fraction. So it says 1 and 2, there are 2 steps. The first fill in the blank says take the percent value and place over 100. So instead of it being 88%, it's going to be 88 over 100. But I would tell you that if you wrote down 88 hundredths, 88 over 100, it's not going to be counted correct. Because after you convert to a fraction, what should you do to that fraction, Alexis? Simplify. You need to simplify the fraction. You cannot just say, oh, perfect. 16% is 16 over 100. Done. 50%, 50 over 100. Done. 413%, 413 over 100. Done. You're almost done. You take the percent and place it over 100. And then you need to simplify. 88 over 100 simplifies to what? Well, we get 44 over 50. 22 over 25. And we're done. To convert a percent to a fraction, you take the percent value and place it over 100. Then you simplify the fraction. That's the first main idea. Are you familiar with this? This is a review from elementary school, hopefully. The second main idea in this part was writing a percent as a decimal. So taking a percent, let's go with what we were working with, 88%. And we want to convert our 88%, we want to take that and make it into a decimal. So to convert a percent to a decimal, take the percent value and you could place it over 100 again. And divide in your calculator. So you could do 88 over 100 and then get out your calculator. Because 88 over 100 is really a division problem, isn't it? 88 divided by 100. That works. Or you can, in your head, divide by 100. You can divide by 100 by moving the decimal 2 places to the left. So instead of 88, here's my decimal right here behind the 88 point. And I can move it 2 places. I can make it smaller by 2 place values, which would be 88 hundredths, 0.88. So again, you're looking at that, you're writing it down so you can review it. Alright, so take 100 and divide, or move your decimal 2 places to the left. Idea number 3. Taking a decimal and writing it as a percent. So let's work with, let's make it a different decimal. Let's make it negative 4.03. There's my decimal, negative 4 3/100. And I want to take that and I want to write it as a percent. So to take a decimal and make it a percent, we're going to do the opposite of making a decimal. So instead of moving it 2 places to the left, we're going to move it 2 places to the right. So instead of negative 4.03, it's going to be negative 403%. And always remember to write your percent sign. That's going to be where most people miss their points. They're going to get to this point, they're going to move it 2 times, and they're going to forget that itty bitty percent sign. Skylar, turn around, please. And the 4th main idea. Writing a fraction as a percent. So let's pretend you took a test, and on that test you get your score back, and your score was 7 out of 50. All right. Not a very good test. So you say to me, Mrs. Long, what grade did I get?
Not an F.
Not a good one.
No. I'll tell you that much.
But how would I tell you to figure out your percent? To convert a fraction to a percent, you divide the numerator, I'll put in parentheses the top number, But you should know by this point in your mathematical career that the numerator is the top number. Divide the numerator by the denominator, which is the bottom number. So you say, Mrs. Long, what did I get? I'd say, all right, well, 7 divided by 50 is 0.14. But that's not your percent. You got a 0%? No, because after you divide the numerator by the denominator, move the decimal 2 places to the, which way? Right. That's multiplying by 100. Because a percent is out of 100. So we just move our decimal 2 times. You got a 14%. Not good. Should you redo that test?
Yeah.
Yes.
That's like a flat out F. If there was an E.
All right. Third hour. So that was review of percents, fractions, and decimals. And that's a pretty big review from elementary school. Now we're moving on to probability. So the counting principle is going to be really important to you. The counting principle says if there are X ways for one event, if I go to Sonic, I can choose from Coke, Diet Coke, Sprite, Sprite Zero, iced tea, Powerade, and Dr. Pepper and Diet Dr. Pepper. So I have 8 basic choices. If there are X ways to do something, there are 8 ways. Then, on top of my basic flavors at Sonic, I can add in different flavors, right? So there are X types of drinks, but then there are Y flavors. How can I figure out how many there are? Multiply them. X times Y. You could put XY. If there are X ways for one event to happen, and there are Y ways for another event to happen, there are X times Y possibilities. What if I added a third choice? I would multiply all 3, right? If I had 8 drink choices and 2 flavor choices and 4 types of ice, I'd multiply all the numbers together. So let's do a little bit of a probability. Let's do a little counting principle. If I have in my gym locker 3 different shirts and 4 different pairs of shorts, how many options do I have to choose from? So what do? 3 shirts times 4 shorts. I could have 12 different outfits before I had to repeat. Let's pretend I add in my 2 pairs of shoes. When I add in my 2 pairs of shoes, I'm going to do 3 times 4 times 2,
24.
Which is 24. The counting principle is actually really important to understand. Because all the time we're looking at how many different possibilities. Is it a good deal? So then we moved on to theoretical probability. And theoretical probability is the number of favorable occurrences. OCCURANCES. The number of a favorable outcomes of occurrences over the number of total. I like to think of it in really simple ways. It's what I want over the total. If I was going to find the theoretical probability of selecting a girl in this classroom, I'd count how many girls there are. 14 girls. Is 14 going to go on top in my numerator or on bottom in my denominator? If I want to pick a girl and there are 14 girls, where does it go? Numerator. It's what I want. What number would go on bottom?
All of them.
The total of all the students, boys and girls. All right, tree diagram. Tree diagrams get really big really fast. I'm going to give you 3 shirts, 2 pants, and 2 shoes. Do you think in this space we have enough room to make a tree diagram? It's going to have to be pretty small. If you don't think you can make it fit in here, where could you turn? To the back. All right. So I've got 3 shirts, 2 shoes. What did I say?
2 pants, 2 shoes.
And 2 pants. All right. I've got a red shirt. What else do I have? A blue shirt. And a striped shirt. There are my 3 shirt choices. Shirt 1, shirt 2, shirt 3. Now what's my next step on a tree diagram? Pants. So with my red shirt, I could wear my jeans, or I could wear my sweats. Am I done? No.
Got your shoes.
Oh, I move on to shoes already?
Actually, no, you have to do it to the other.
Oh, my blue shirt, I could wear my jeans or my sweats. And then my striped shirt, I could wear my jeans or my sweats. Am I done with shirts?
No.
Am I done with jeans or with my pants? Now what do I move on to?
Shoes.
All right, so with my red shirt, I could wear my jeans. My red shirt, my jeans, and my Converse. And I heard ballet shoes. So red shirt, jeans, and Converse. Or red shirt, jeans, and ballet shoes. Then I'd go to my sweats. Red shirt, sweats, and Converse. Or red shirt, sweats, and ballet shoes. Am I done? Do the same thing. Blue shirt, jeans, and I'm just going to put a C for Converse and a B for ballet because you get lazy at this point.
I was lazy before this.
Converse and ballet shoes. Converse and ballet shoes. Converse and ballet shoes. So what's the pro of making a tree diagram? What's the purpose? Why would we ask you to make a tree diagram? What is What's the purpose behind creating a tree diagram? It's a visual of how many choices we have, right? If I said, is it possible to wear blue shirts, sweats, and ballet shoes? Can you look at this and figure it out? Yeah, blue shirt, sweats, and ballet shoes. You can visually see it. Colin, please face the front. The counting principle tells us 3 times 2 times 2, which is 12. Are there 12 outcomes? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 outcomes. The counting principle is much faster than the tree diagram. But the purpose of the tree diagram is so you can visually see all the choices. Dependent events. Raise your hand. Who can tell me something about dependent events? Dependent events. Events where the probability of the first event, blank, affect the probability of the second event. Dependent events. Tell me about it, Luis. Dependent.
Where the first event affects the.
It will affect the probability of the second event. Dependent events. It will. It's going to change. Dependent events tend to be without replacement. If I went to go play bingo, all of the bingo balls are inside that big cage thing that they spin around, right? Mm-hmm. And the first bingo is drawn and it's B11. Does that B11 go back inside? No, that B11 goes to the side because it's already been drawn. Bingo is dependent probability. Because then the next time, if there were 75 bingo balls, now there are only 74 bingo balls. And they spin it and it's 075, so they take that out. Does it go back in? No, it goes out to the side. So there, we started with 75. Then we went to 74. Now we're at
73.
Dependent probability. Independent probability. It will not affect it. It does not change. Independent probability is with replacement. Or maybe there's not even replacing things. The lottery, the Powerball is independent. Each number in the lottery, each ping pong ball with a number on it comes from a different machine in the Powerball. Each machine has 74 numbers or however many there are in it. Independent is with replacement, or they're things that don't matter to each other. Flipping a coin and rolling a die. Do those two share anything? No, so they're independent of each other. Experimental probability. What do you have to have in order to have experimental probability? What do you have to do? An experiment. You have to actually do it. It's different than theoretical probability. Experimental probability doesn't always work out the way you want it to, right?
Yeah.
So it's the number of times it happens, the number of occurrences, and the number of trials. If I flip a coin 10 times, does 10 go on top or 10 on bottom? Because that's my number of trials. If I flip a coin 10 times and 9 of them are heads, I'm going to have a probability of 9 over 10. Do you expect that to happen?
No.
No.
It's a coin.
Experimental probability does not always match the theoretical probability. Hence, predicting probability. I'm going to give you a math problem. Are you ready? I'm going to give you a problem to solve. Here's my name. What is the probability of drawing or picking a vowel? 1 out of 4. Because there is one vowel, an O, and there are 4 letters. So let's pretend I have L, O, N, and G in a bag. And I ask you to pick one, record your data, put it back. And I ask you to do that 57 times.
Oh.
How could you predict what do you think will happen? Could you predict how many times you think you would draw out you'd pick the letter O? Okay, so I heard 2 things. I heard Colin say it's a quarter because it's 1 out of 4, right? So Colin's probably looking at like, okay, 57 divided by 4. What's a quarter? How do I take 57 and equally break it into 4 groups? Right? So you could look for equivalent ratios. If this wasn't 57, if this was 40, would it be easier? If it was 40, what would you do? Yeah, I'd know 4 times 10 is 40. So 1 times 10 is 10. Done. But it's not 40. It's 57. So equivalent ratios doesn't always work. It works, but it doesn't always work. What's the other way that you could figure it out? Cross multiply. One times 57 is 57 equals 4 times an unknown what do you get? Compound probability. Compound probability gets really big really fast. I went to a fundraiser over the weekend, and one of the games that they played at this fundraiser to raise money for the school was they played this game called Heads or Tails. So you paid $5, and you got to play the game multiple times, and the game was they flipped a coin, and you guessed if it was going to be heads or tails. And if you won, you got to keep playing, and if you lost, you had to sit down. So, flip a coin, you picked heads or tails. So when I did that, right, I had a 1 out of 2 chance of being right, correct? And the first time I was right. I won. The next time they're going to flip a coin. What's my probability the next time of being right? 1 out of 2. I was right again. The third time, what's my probability of being right? Still 1 out of 2. I'm picking. It's either going to be heads or tails. This time, I never got past the 3rd round. However, there was one round where it went 8 times. They got it right 7 times. 1, 2, 3, 4, 5, 6, 7. So these two people, they had been right 7 times in a row. Do you know what the probability of being right 7 times in a row equaled? 2 times 2 is
4,
times 2
8,
times 2
16,
times 2 times 2, 64 times 2, 128. They had a 1 out of 128 chance of being right 7 times, and they were. 2 people were right 7 times in a row.
One chance.
What did the winner get?
So they had to go a third or an 8th time. So it went from being right 1 out of 128. They had to be right 1 out of 256 times. And if they both would have been right that time, it would have doubled again. Compound probability is the probability of an event times the probability of an event, ... This is why understanding probability is so important. If I was right 3 times in a row, do you think I'm going to be right that 4th time in a row?
Probably. There's a very slight.
Oh, I got it. I was right 4 times in a row. Do you think I'm maybe going to be right 5 times in a row? Maybe.
No, did the winner get anything?
They won a gift card.